This Fizzcast is looking at a macroscopic version of a 1D infinite square well. Pause the video and read through the question carefully. Now that you've read through the question, you should see we've got a particle of a particular mass, in this case an ant that's 5 milligrams, and it's somehow constrained into some particular region of space. In this case it's inside a matchbox with a length of 4 centimeters. And it's moving backwards and forwards between the limits of this particular constraint at a constant speed. And as this question says, we're going to treat this as a one-dimensional infinite well problem. In other words, somehow this ant is unable to break through the walls of the box. It's definitely constrained. It would require infinite energy to somehow get out of the box. That's an approximation, but it's an approximation that we should be able to use our understanding of the quantum mechanical treatment of an infinite square well. So let's think for a second what that looks like. We've got some kind of region of space here. We typically would call this distance along here perhaps A, which in our case we're told that's 4 centimeters. And we'd have some particle, in this case it's an ant, that's able to move freely within that space. So it's moving at a constant speed. There's no net external force acting upon it. It's not accelerating or changing its speed. But it can't get out. So it's basically constrained to be within that region of space. And if you go back and look through your lecture notes or any other reference you know about infinite square wells and the quantum mechanical treatment of that, you should be able to figure out that the energy levels that are allowed are only certain allowed energy levels. The ground state E1, and then E2, and then E3, etc., etc. Where those energy levels are dictated by some integer n, and it's that integer squared multiplied by the ground state level. And then you have to recall that that ground state level can be given in terms of some of these quantities here. It's actually the square of h bar multiplied by pi squared, all divided by twice the mass of the particle times the square of the size of that 1D well. So they're the allowed energy states. And what do we know about the energy of state of this particular ant in this particular matchbox? Well, the only energy it possesses here is kinetic energy. And it's going sufficiently slowly here that we should be able to be quite comfortable using a non-relativistic form of its kinetic energy. So its kinetic energy here will be equal to a half the mass times the square of the speed. And what we're looking is for these particular values that we have for this particle in the box, for this ant in the matchbox, what's the value of this integer n here? How far up this energy scale must we be for this particular system? So we should be able to rearrange this expression here reasonably straightforwardly to show that n squared, for example here, must be equal to 2ma squared over h bar squared pi squared multiplied by a half mv squared. And my half and my 2 there cancel out. In fact, I've got an m here and another m, so it turns out I'll end up with a bunch of things squared. I'll end up with an m squared v squared a squared, all divided by h bar squared pi squared. That's n squared. That's the square of this integer. So really quite straightforwardly, I can show that that integer must be equal to m times v times a divided by h bar times pi. It's worth maybe stopping at this point to make sure we've got this expression handled correctly, that we haven't done anything ridiculous along the way, that our initial kind of equality that we put there did make sense. This quantity n here, of course, is supposed to be an integer. It's telling us which one of these energy states, these allowed energy states, we are. It's kind of an index of the energy states, which means that this quantity that we've just made it equal to must also be a dimensionless quantity. It must have no units. So let's just double check that that's the case. We've got our mass here. Let's put that in SI units of kilograms. We've got a speed here. We can put that in units of meters per second. And this A here, you'll recall, is the width of our well. So that will be in units of meters. That's a distance. And we're going to divide that by Planck's constant on 2 pi multiplied by pi. Well, those factors of pi don't have any units, but that Planck's constant there has units of joules times seconds, joule seconds. And then we might want to recall what a joule times a second gives us. A joule, you have to remember, or you might go and look up here and say, well, I know that energy is in joules, so it must have units of kilograms meter squared per second squared. There's my joule, and of course I've got a joule second, so I'm going to multiply that by seconds. And then let's double check that our kilograms cancel, top and bottom. I'm going to have a metre times a metre on the top, but I've got metre squared on the bottom, so that metre squared on the top cancels with that metre squared on the bottom. I've got per second on the top, and I've got per second squared multiplied by seconds on the bottom, which of course gives me a per second. And so in fact those units of time there also cancel, and what I'm left with is no units whatsoever, which is a nice kind of intermediate check I can make here, that I haven't done anything too silly. Again, it doesn't tell me that I've got exactly the right expression, but it tells me that if I've been consistent with my rearrangement of equations here, that I have in fact got the right expression for that rearrangement. And now I can just place some values into this expression. The mass here, we're told, is 5 milligrams. You have to remember that 5 milligrams is 5 by 10 to the minus 6 kilograms. Remember, a milligram is 1,000th of a gram, but a gram is 1,000th of a kilogram. And we're going to do this in SI units here, so everything cancels out nicely. And our speed, so that's our mass, our speed now is 0.12 meters per second. Our size of our box is 4 centimeters, so let's put that there as 0.04 meters. And we're going to divide that by Planck's constant on 2 pi, which you might get used to writing down as 1.05 by 10 to the minus 34 in units of joule seconds, multiplied by pi. And if you do that calculation, and I've just done that on your calculator, you'll find, of course, let's just have a quick look before we do the value. On the top line here, we've got, say, something like 10 to the minus 6. This speed here is something like 10 to the minus 1, and this distance here is something like 10 to the minus 2. So there we've got maybe something like 10 to the minus 9, something by 10 to the minus 9 on the top line there, which is quite a small value. But on the bottom line here, we've got 10 to the minus 34. So clearly the bottom line here is way smaller than the top line. Having a small value on the bottom line gives us a large number overall, and that's what you might expect. And when we do that calculation, we're going to end up with, I say, something like 7.3 times 10 to the power of 25. That's our value for n. Of course, that should be an integer. We don't have enough precision given to us in the question to know what all these other significant figures will be, but that quantity should come out to be an integer. It has no units, so we don't have to write anything out here. That's essentially the answer to the first part of this problem. What's the integer value n, the quantum number for the ant running backwards and forwards in this box? And it's an enormous number there. It's not like 1 or 2 or 10 or 100. It's 7.3 something 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 something, because a whole bunch of significant figures there that we don't know at the moment, times 10 to the power of 25. So as you might expect, quantum mechanics is kind of expected to be really important and reveal some interesting behavior when you're down at things like the atomic scale. But even something as tiny as an ant running inside a matchbox is still way too large for us to expect some kind of low-lying energy state. This is a very high-lying energy state. And to get a bit of a feel for why this quantum mechanical approach wouldn't be expected to reveal anything kind of observable in this system, let's think about the second part of this question. The second part of this question is asking about the distance between the peaks in the ant's probability function. So again, you might recall, if we think about what those allowed energy states look like, the ground state, the n equals 1 state would look something like this, and then the n equals 2 state would look something like this. What we're really interested in, of course, is the probability function, which would be the square of those. So our ground state 1 might look like this, the n equals 1, and the n equals 2 might look like this kind of thing, and n equals 3, etc. And you can see, as you might remember, that the number of peaks we see in this probability distribution scales like the value of n. So for the n equals 1 state, there's 1 peak. For the n equals 2 state there were 2 peaks. So for this n equals 7.3 by 10 to the 25 state, we would expect to have that many peaks in our probability distribution. So we should be able to figure out the distance between adjacent peaks. Will be quite straightforward. That distance between any two peaks in our distribution there, let's call that maybe d. D there must equal, well, the size of our box, 4 centimeters, divided up into this many parts. So 7.3 by 10 to the 25. And that will give us a value. You can see again, it's going to be a very, very tiny number. I say of something like 5 by 10 to the minus 28 of a meter. And that's the scale upon which we could expect, if we were to observe the ant, there'd be places where the ant would be very likely to be. They would be the peaks in this probability distribution. There'd be places where the ant was very, very unlikely to be. There might be these kind of dips in that probability distribution. And those things are roughly half this distance apart. And so that would be nothing that we could ever expect to have an observable kind of impact upon our observations, because that's just such a ridiculously tiny distance. Again, way, way smaller than the size of a nucleus. So although we think we can describe infinite 1D well systems by this quantum mechanical approach, and we do expect to see things on the scale of atomic and molecular systems, even if they do apply, and we think these theories do apply generally, there'd be no real measurable or observable features due to this quantization. But interestingly, it's a fairly straightforward application of this general idea at the top here of these quantized energy states that go like the square of an integer multiplied by the ground state.